This video covers energy and physical pendulums. So remember, we've talked about energy before in terms of springs. Now the total mechanical energy is still conserved for our simple harmonic motion example of a spring with a constant K, mass M, and on a frictionless surface. So remember that E is equal to kinetic energy plus potential energy, which is 1/2 mv squared. And again, the potential energy we're going to have in this situation is 1/2 kx squared. So the particle has all potential energy at x is equal to a. Again, we're not moving at that point, so all of our energy is in the form of potential energy. And the particle has purely kinetic energy at x is equal to 0, again, when we have no stretching or compression. So again, at the turning points, which is at the maximums here, amplitude, the maximum amplitude, and negative a, all of our energy is in the form of potential, so which is 1/2 x k, and then our x is actually the amplitude in this situation. Now, at the middle point, which is our equilibrium, we're going to have entirely kinetic energy, which is 1/2 velocity maximum squared. So we know that in terms of conservation of energy, they should be equal to each other. So what we have at the very bottom, when we get V max by itself, is we have an equation for velocity in terms of amplitude, spring constant, and mass. Again, it is possible for you to see these types of graph on the multiple choice section of the AP exam. So I want you to notice what's happening here. We do have entirely potential energy here. So here we're seeing a energy graph, our potential energy graph curve. So as we approach our equilibrium, we start to decrease in potential energy. At the middle, we have exactly 0 potential energy. As we move away from the middle towards our other maximum, then our potential energy starts to increase, and that happens back and forth. So you see that this is kind of like a skateboarder on a ramp, just going from one point to the other. Okay, but you do see here that our total energy stays constant all the way through. Total energy does not change. That means my kinetic energy function is going to be this, but flipped. At the middle, we will have maximum kinetic energy. And then at these points, it's going to slow down. Okay, so you have this inverse of this potential energy graph. So here, what I've drawn in pink is our kinetic energy curve. So we know that as we approach our ends, that we start to slow down and then reach our maximum. So at that point, we have no more kinetic energy. And then we can come back towards the center and reach our maximum kinetic energy here in the middle. Now, you won't see multiple springs very often. I've rarely seen them happen, but it is in the curriculum, so I'm going to go ahead and cover it. If you have multiple springs, you notice that these equations look very similar to that of circuits, that if you have 2 springs that are in parallel, meaning they are connected to each other, like shown in this picture, then the way that you will add them is simply add them. Now, in a series, which is opposite what we did in circuits, we're actually going to add the inverses. Now, for this one, it's important that you get the inverse and then add it to an inverse. You cannot add K1 and K2 and then get the inverse of that. That's not how that mathematically works. Here, our compression distance will be the same. So again, if they're attached next to each other, if I were to press on this square, it's going to compress the same distance here and the same distance here. If I compress on this square in the series, then you will have this relationship. x1 over x2 is equal to k2 over k1. And again, x's represent compressions in this case, or stretches. And then the energy stored within both of these springs is going to be related by these equations here. Again, it's going to be the same for both, but it's important that you do recognize that there is a difference in subscripts. Lastly, I want to use the rest of this video to show a very important topic that almost always comes out on the AP exam free response section. So if the net force acting on a particle is a linear restoring force, the motion will be a simple harmonic motion around the equilibrium position. And we'll see a couple of examples of what that means. So here I'm going to show the equation of motion for a mass on a spring, but we're going to draw a few pictures first. So let's imagine a spring mass system. What that means is here I'm going to have a spring attached to a mass, and I'm going to pull it away from equilibrium position and then allow it to oscillate. Now we know that the force that this spring experiences is equal to the force of a spring is equal to negative kx. Now this is the only force acting in the x direction. So we know that the sum of the forces is going to be equal to mass times acceleration. So here, we want an equation that relates x and a, if we want to be able to solve this. So that means, if you remember, that acceleration is the second derivative of position with respect to time. So now I have here an equation x, or a variable x, and a second derivative of that x. Now, if I rearrange this and clean this up, I'm going to move m to the other side. And I get the second derivative of position with respect to time is equal to x times negative k over m. This is the equation of motion for a mass on a spring. And we'll do a few of these examples in class. Now, we said that a linear restoring force is going to cause simple harmonic motion. So the force that causes simple harmonic motion here is this spring force. And this negative tells us it's a restoring force. So it is always opposite the direction of the displacement. Now, that form of equation is a second-order differential equation. So unlike algebraic equations, their solutions are not numbers, but functions. In simple harmonic motion, we're only interested in one form, so we can use our solution for many objects undergoing simple harmonic motion. Solutions to these differential equations are unique. There is only one. One common method of solving is guessing the solution that the equation should have. So again, here down at the bottom, I have my equation of motion for a force, a mass on a spring. Now, I can guess that my equation, x is equal to a cosine of omega t plus phi, is a solution to this second order differential equation. Which means if I were to use this as my function of x, then I can actually solve for, let's say, an angular frequency. So if we go back to that equation, then we can see how we're actually going to apply it. So again, negative k over m x is equal to the second derivative of position with respect to time. Again, our function is x is equal to a cosine omega t plus phi. Now, I can put that function in for x, and I get negative again, the second derivative of this function is negative omega squared a cosine omega t plus phi. Now, here you can see that this a cosine theta, this a cosine piece, and this a cosine piece will cancel out because they're the same function. So all I'm left with is negative k over m is equal to negative omega squared. Now, the negatives will cancel, and I'm left with the square root of k over m is equal to omega. Now, this is always true. That's how we got our other equation for period. So we said in our last video that omega is equal to 2 pi over t. Well, let's say I want to get t by itself. That means I'm going to multiply by t, and then I'm going to divide by the square root of k over m. Because I have a fraction down here at the bottom, this turns into 2 pi square root of m over k. So that's how we got our equation. But on the AP exam, they're going to ask you to derive this piece, this equation of motion for a mass on a spring. And the reason that this equation works out is because our force is variable. It changes with respect to position. Now let's do something very similar for the equation of motion for a pendulum. For a pendulum, we have an object on a string. Initially, it is pulled away from equilibrium and has an angle theta that it makes with the vertical. Again, the free body diagram for this object, we have mg going down, we have t going along the string, and then we normally get the components. Now here, it's going to be mg cosine and mg sine. Now, as this object oscillates back and forth, this theta is actually changing. So this force, mg sine theta, actually changes. So let's look at only mg sine theta. So we're saying that our coordinate system is like this. Okay, this is x and this is y, and we've done this before. Now, because mg sine theta is always changing, it's always opposite the direction of my displacement, similar to my restoring force of a spring. So this is negative mg sine theta. Okay, again, you can also say it's negative because it's going to the left. So we'll have negative mg sine theta is equal to mass times acceleration. Again, we can rewrite acceleration as mg as a second derivative of position. But now you can see that here we have a theta and here we have an x. So we need something that'll relate the two. Before I do that, I'm going to cancel out these m's. And what I'm going to apply here is a small angle approximation. And I'll talk a little bit more about this in class. Now, what the small angle approximation says, that if my angle is small, something less than 10 degrees, then the sine of theta is approximately equal to theta. And the cosine of theta is approximately equal, and again, we'll show proof of that in class. So here, in problems, it will always tell you, use the small angle approximation. It will say that, and we'll see problems like that in class. So that means I can replace this sine theta with just theta. Now the problem is I still need to relate x and theta, but we know that x is equal to r theta, because really this object is moving in at least a piece of a circle. Okay? So we can replace theta with x over r. So this is x over r gives me theta. So I'm going to replace theta with x over r. Now my r in this situation is going to be the length of the string. The reason for that is because the point at which the string is attached is technically considered my axis of rotation. So this is the equation of motion for a pendulum. Now we can go one step further and find the solution to this. And by doing that, we can apply the same reasoning that we did before, that x will be a cosine omega t plus phi, if we need one, and negative omega squared a cosine omega t plus phi. Again, the a cosine omega t's will cross out, and what we are left with, though, is negative g over L is equal to negative omega squared. Again, here the negatives will cancel out, and we're left with the square root of G over L. Now we can also derive that other equation that we gave you for the period of a pendulum if we say that this is equal to 2 pi over t, and we get t by itself. So that gives us t is equal to 2 pi L over G. Again, showing where these equations are coming from and not just necessarily giving them to you. Again, in class I'll show you examples of what this problem might look like and what it might say in order for you to know this is the solution or this is the process you're going to be showing.